Okay. So let's look at f of, yes, please.
So just like methodology.
Yes.
So when it says, find all the solutions, we have like 7 pi over 3. And it's like find everything.
Yes.
So like methodology, do we
Yes, let's do that.
Reference angle?
Let's do that. Let's do that first before we look at tangent.
Okay.
So give me any angle. I prefer an angle that we can identify.
Yeah.
But you can say, I'm giving you sine to be 1/4, determine the other ones.
Sure.
That's one type of question. Or you can say, here's the angle, find all 6 trig functions. Which type of problem you want to look at?
Yeah,
One more time.
Find all 6 trig.
Okay, so let's find an angle. Can anyone give us an angle? It can be anywhere on the unit circle. Any quadrant. Make one up. Degrees, radians, whatever you want.
36 degrees.
How many?
36.
But I can't.
Oh, one that we can.
Yes.
Oh.
So it has to be either a multiple of 30 or a 45 or a 60. So we can identify them based on the little chart that I asked you to memorize, of those 3 numbers.
120.
Okay, very good. So alpha is 120 degrees. Perfect. So we are asked to find sine 120 degrees, cosine 120 degrees. Is that what we're trying to do, Nico?
Yeah.
Okay, very good. So once I have sine and cosine, you understand that the other 4 will not have any problem. I will not have any problem to find those.
You just say you need to memorize like what sine and cosine and all of the functions.
Right, those 5 numbers actually. So let's do it slowly and then why is this important? You can say, wait a minute, I can plug into the calculator. Why are you torturing me with the square root of 3 over 2? It's because of what follows next in math. So I'm hoping that at least these 5 numbers will be clear and you don't have to plug in. It's like I see my students in 011, they plug in the calculator 3 minus 2. So this is the 3 minus 2 that we should not need to plug in trig moving forward. Okay, not because I want to torture you with these 5 numbers, but we should have the basics. And this is like the ABC of trig, those 5 numbers. Okay, yes, you can always plug them in the calculator. Okay, so first I have to identify where the terminal side lands. Because if I don't know where the terminal side lands, I will not know the sign of sine and cosine.
Right.
So is that clear?
Yeah.
Okay, so I know that this is 180 degrees. And we picked 120, so it has to be 60 shy of 180. So 60, remember we are divvying up, although this is my graph cannot be exact, but I know that this piece has 30, 30, 30, because it's 90, and the angle should stop here. I'm not expecting, and I'm not going to look at this with a magnifying glass, but if you show that 120 is here, something is not right. Okay? So show that you divvy up the quadrant in 3, and this is your 120 degrees. So what will this piece represent from here till here?
Sine.
Exactly, sine of 120. Very good. What will this piece represent from here till here? Yes. So sine is in green and cosine is in orange. Obviously, sine will be what type of number? Sine is the green.
Yeah, positive.
Right, because it's measured on the y-axis. It's the height of the point, right? The y-coordinate of this point. So it has to be positive. What about this orange piece? Right, because it's in that direction. Right, so we know that cosine will be negative, so I can already write the sine, and I know that the sine will be positive. And now I know tangent and cotangent must be negative. I know that cosecant must be positive, and secant must be, right? I already know this information, correct?
Yes.
Good. So then I find the reference angle. So what is the reference angle?
60.
Yes.
Or 5.
Yes. When I start with 120, I will keep now everything in degrees. Now, if you want to change it into radians, then you will have to write 2 pi over 6. I'm sorry, I meant 3, of course. It's up to you, but keep it all either in degrees or all in radians. Good. So now the answer here will be sine 60 degrees, and here will be cosine 60 degrees. And now I'm ready to identify what they are. Is this okay so far?
Yeah.
Okay. Once I establish the sine, then I can say sine 120 is the same with sine 60, because it's this piece. So then how much is sine 60? And sine 60 is the last angle. So you remember 1/2 and the square root of 3 over 2, and you have to remember the square root of 3 over 2 1/2. The square root of 3 over 2. And what will be cosine? And of course with minus. Is this okay?
Mm-hmm.
Now, do we have to determine the other 4?
Yes.
Okay.
Yeah.
Yes, very good. So tangent 120 degrees is this over this, which is negative the square root of 3. Cotangent 120 degrees is 1 over this, which is negative 1 over the square root of 3, and I have to rationalize it.
Oh, it's good.
Secant is 1 over this. I flip it, negative 2. And cosecant 120 is 1 over this, which is 2 over the square root of 3, and I have to rationalize. Once I have sine and cosine, there are no more secrets. And always keep it as simple as possible. Always think in terms of sine and cosine. And always think in terms of positive angles, because you know the properties. That's one of the reasons why we studied odd and even functions in chapter 2. More so for trig than really knowing that a polynomial function is odd or even, or a rational function is odd or even. That was really preparation more for this. Okay, very good. Anything else? Very good question. Nico, you have anything else? Is it clear how we determine the other 4?
Yeah, so we need to know.
So tangent is this over this.
Yeah.
Cotangent is the reverse of this, rationalized. Secant is 1 over cosine. And cosecant is 1 over sine, and after that, rationalized. Better?
Yeah. But if they give us, give us like something like pi over 4, and then we need to find the trig function, do we first? Or what if you give us, what is
You want to choose another angle?
yeah, what was the radians of 120? If you give it to us in radians, then we find like the reference.
Yes, because remember, pi over 3, pi over 3 is 60. 60 times 2 is 120.
Okay, so then we would try to find the reference angle. And then
Yes.
same
The
way.
reason why you have to find the reference angle is because first you have to know where the terminal side lands, because it can land anywhere on the unit circle, and based on that you will know the sign of those trig functions. And once you have the terminal side, then you will be able to immediately identify the reference angle. Without the reference angle, we don't know. You can say, yes, I'm going to put in the calculator. Calculator will tell me sine of 120. True. But basically, 120 is not an angle that can fit in a right triangle. So we stick with the rules. Opposite over hypotenuse. How can a triangle with 120 degrees have an opposite and a hypotenuse? Opposite leg and a hypotenuse? It can't. So that's why we have to go back to basics and find the reference angle. Good. Anything else? Very good question. Anything else? Do we need another example or something that you were thinking about, or we go back to tangent? We have to talk about tangent and its inverse. Okay, tangent then. So remember when we fill out that big table, Big table. We didn't even finish it in one session, right? We had to continue. Okay, what did we find for sine and cosine? No problems. But when we got to tangent, several times we wrote something we don't like. What did we write? Right. Why is that? Here's why. Sine is a ratio. Well, you can say, wait a minute. Sine, tangent is a ratio. But wait a minute, you can say to me, but sine is a ratio as well. It's the opposite leg over the hypotenuse. Yeah, but none of them can be 0, because otherwise the triangle doesn't exist. So although they are ratios, they can be undefined. Because if the hypotenuse is 0, then there is no triangle, there is no sine. However, look at tangent. What has to happen for tangent to exist? Exactly. If cosine x does not equal 0. Now, let's think on the unit circle. Where is cosine 0? Cosine is measured on the x-axis?
90 and 270.
Exactly. So that's where the function will have, yes, how do we call it? We graphed those before in rational functions.
Oh, vertical asymptote.
That's it.
Oh.
That's it. Cosine is undefined. Tangent is undefined when cosine is 0. And you already told me when x equals 90 degrees or pi over 2, and when you also said 3 pi over 2. But of course you have to go in the negative direction as well. You have to say negative pi over 2 and negative 3 pi over 2 and forever, right? So vertical asymptotes all over the place for tangent. So, like last time, we have pi over 2. We have pi, 3 pi over 2, 2 pi. Negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. 3 pi over 2, negative pi over 2, pi over 2, pi, 3 pi over 2, and 2 pi, and I can go on forever. You already told me the vertical asymptotes one more time are where? Of course, and on the other side, a negative pi over 2. And then, and negative 3 pi over 2. And of course, forever. Okay, now, what quadrant is this between 0 and pi over 2? Yes. What is the sign of tangent in the first quadrant? Very good. What quadrant is this? I just wrote a sign. You don't have to do that. I just, yes. What is the sign of, okay, good. What quadrant is this? Say it again.
I thought you said quadrant 2.
Yes, and tangent is negative there.
Oh, okay. You said tangent. Okay, you said
Tangent is negative because cosine is negative. Good. What quadrant is this? Good. What is the sign of tangent there? Correct. And so on and so forth. And here, and what about this one? What quadrant is this between negative pi over 2 and pi? What is the sign of tangent in there? Correct. So here's the graph. Asymptotically getting closer and closer to the asymptote. We know that. My graph is not perfect, as you see. Sorry about that. And it goes on forever. And this is the graph of tangent. I should have asked you, what is the tangent at pi? Forgive me. Tangent at pi is sine pi over cosine pi. How much is sine pi?
0.
Very good. How much is the cosine pi?
1.
Negative 1.
Yeah.
But still, 0 over negative 1 is still 0. Okay, what about at 0? How much is tangent at 0? How much is sine at 0?
0.
How much is cosine at 0?
1.
So 0 over 1 is 0, and so on and so forth. So this is the graph of tangent x. It has infinitely many vertical asymptotes. Why? Because cosine can be 0 in infinitely many different situations. And of course, you can continue forever to the left and to the right. However, we want to create an inverse function. So we will have to do something about it, because this is not one-to-one. By the horizontal line test, this is not one-to-one. So we will have to diminish its domain. So we are going to diminish its domain between negative pi over 2 and pi over 2. Is there any other function whose domain was diminished to negative pi over 2, but including negative pi over 2, pi over 2, not excluding negative pi over 2 and pi over 2? Is there any other function? Exactly. So not difficult to remember. So let's look at those, because I'm trying to embed this in your system. Okay, so here is for sine. And sine inverse. Here's for cosine, right? And here's for tangent. That's all we need when it comes to the inverse functions, basically. Depending on problems and so on and so forth, but this is good enough. So can anyone give us the domain of tangent and the range of tangent? So tangent is defined on
Negative pi over 2. To pi over 2.
and the range. Let's look at the graph. Range, we're talking about the range.
Negative 1. But it doesn't include
Asymptotes. When we talk about asymptotes, what do we mean?
negative infinity to infinity.
Of course.
Yeah.
When we talk about asymptotes, there is no stopping. When we talk about vertical asymptotes, there is no bound, right? Otherwise, it will not have a vertical asymptote. Remember the definition of the vertical asymptote: when the function blows up, we say, or goes down to negative infinity or goes to positive infinity. That's the definition of the vertical asymptote. Is that okay? Very good. So now tangent inverse. I need domain and range.
Negative infinity to infinity.
Right.
Pi over 2. Pi over 2.
Yes. We have to graph the inverse function. Extremely important function for Calc 1 and beyond. Both. Okay, now let's also write what I said and I didn't write. Period. For all functions one more time. For sine, for cosine, tangent, cotangent, secant, cosecant, although we have not graphed secant, cosecant, and cotangent yet. So we said all of them have what period?
2 pi.
Yes. 2 pi, 2 pi, 2 pi, 2 pi. Before you say anything about tangent, let's look at the period for tangent.
Pi over 2.
Right, which is pi. Yes. The same with cotangent. These are the only two that have the period pi. In other words, I will see everything they can offer over a pi. But if I want to look at sine, cosine, secant, and cosecant, in order to see everything, I have to show it over 0 to 2 pi, or on a 2 pi range. Okay? Good. So I'm going to graph just the main portion. So this is negative pi over 2 and pi over 2. These are the vertical asymptotes. X equals pi, negative pi over 2. And the other one, x equals pi over 2. Here's the graph of tangent. The graph of tangent x. Before we graph the inverse function, let's come back here. Tangent, because of the parentheses, very clearly, they state that x equals negative pi over 2 and x equals pi over 2 are, one more time, vertical asymptotes. And the range is anything. Okay, now let's look at this function, tangent inverse.
Horizontal asymptotes.
Exactly. Which are,
Negative pi over 2 and pi over 2.
very good, that's all I want you to notice. Ah, sorry. What type of function is tangent? In symmetry-wise?
Odd.
Right. So will its inverse. So this is a function f of x, tangent inverse. It has another name as well. Arc tangent x. So you can find tangent inverse, which does not mean 1 over tangent. We know that.
Yeah.
Okay. Or you can find it denoted by arc tangent. Arc tangent. Okay, I would like to go back to 5.3 for some examples and then come back to 6.4 to finish that. There is no amplitude for tangent. There's no such thing as called amplitude for tangent. The amplitude is only for sine and cosine. Let me write this down just to make sure that we don't get confused. Amplitude only for sine and cosine.
So not secant or cosecant either.
No other function has amplitude, just sine and cosine. I want to draw your attention to the fact that tangent, function tangent is in 5.4, section 5.4. Okay, let's say we want to look at 29. I would like to look at some graphs. Y equals, this is on page 405, y equals pi, I meant to write tangent pi over 4x. Here we are asked to find the period and graph the function. Okay, so I'm going to copy it one more time because it's not very clear here. Y equals tangent pi over 4x. This is the argument. The book does not put it in parentheses. It does not need to be in parentheses. But I don't want you to think that this is tangent pi over 4 and then multiplied by x, because it's not. It's tangent applied to pi over 4x. Good. So first we have to determine the period. Exactly how we did it to sine and cosine. But this time is not 2 pi over, but it's pi over the number that multiplies x. For sine and cosine was 2 pi over the number that multiplies x. So pi over what? Pi over 4. I have to flip because the top is pi over 1 times the denominator flipped pi 4 over pi. I simplify by pi and I get 4. Any questions on finding the period? Any questions? Okay. Next, before we graph this function, I'm going to ask you a question. Is pi over 4 a number smaller or greater than 1? Here's why. If pi over 4 you're going to say is greater than 1, then the graph does this. Horizontal shrinking.
Right.
If it's greater than 1. If you say pi over 4 is a number smaller than 1, then the graph will do this. Horizontal stretching. Not by much, but horizontal stretching. We're going to graph both functions. Plane tangent and tangent pi over 4 to observe this thing. So is pi over 4 smaller or larger than 1?
Small.
It's smaller than 1. So then the graph, original graph, would be between negative pi over 2 and pi over 2. But this one will be a little bit wider because the number in front of x is smaller than 1. So let's plug in both in y equals. I have to change my mode again because, as you know, oh no, it's in radians, that's fine.
So it'd be between -2 and 2.
It will be
If it's normally between.
between -2 and 2. Correct. So y equals, I want to graph tangent, x, and we're going to graph the other one, tangent, pi over 4. You can write it as pi x divided by 4. It's the same thing. Or if you write it as pi over 4, you have to put more parentheses.
Yeah.
So be careful. So I preferred multiply the tops, pi x, and divide by 4. Now the viewing window, I don't want to see the whole thing. So the viewing window, let's put it between -2 and 2. And really it doesn't matter. Y minimum, Y maximum, it doesn't matter because they go to infinity anyway. And let's see what happens. We're going to see a little bit more, right? So disregard these pieces because they are part of the next portion, the next graph. So as you see, this is the tangent. And as you see, the red graph is a little bit wider, as expected, because that number pi over 4 is smaller than 1. I really needed this when I illustrated that horizontal shrinking and stretching, but we did no trick then, because this is a perfect illustration. Any questions? So as you see, the vertical asymptote here is at -2, but the vertical asymptote for this is at negative pi over 2. And the vertical asymptote for this portion is pi over 2, but the vertical asymptote for the red graph here is at -2, a positive 2, of course. Any questions? Okay, so let's look at one more. Yes, 39 on 405. Here I would like to determine the phase shift and the period. So tangent, so y equals tangent twice x plus pi over 2. So I want the period and the phase shift. 39. Did I copy something else? I'm very good at doing that.
That's on the calculator.
Oh, sorry. So here I want the period and the phase shift. without doing anything, which one will you determine first? The phase shift or the period? It doesn't matter really, but which one is easier to determine right away?
Phase shift.
Right, what is it?
To the left by pi over 2.
Yes, and we write negative pi over 2. Perfect. What about the period? Because remember, when you identify the phase shift, the leading coefficient here must be 1. If it's 2, then you have to pull it out first.
Right.
And that was ready for us. So what about the period? Because it's tangent, I have to write pi. But what do I write in the denominator? Exactly, because 2 is the number that multiplies x. So that will be the period. Because 2 is the number that multiplies x, what did you expect this function to do? Did you expect it to do this, a horizontal stretching or a horizontal shrinking of the graph?
Shrinking.
Yes, and that's what it is. Look, from a period of pi to a period of pi over 2, it's definitely a horizontal stretching. Horizontal shrinking, I meant to say, of the graph. Although this 2 outside gives us the impression that it will be doing this, but no.
So would it ever make sense to shrink that 2 back inside?
Only if you want.
Just to
If you want to put in the graphing calculator and you don't want to put 2 outside and parentheses again, because the calculator will require another parenthesis here. So you would write it as tangent 2x plus pi. Unless you want to put nested parentheses in the calculator.
Well, I'm saying, would we get the same phase shift if we did that?
Yes. I mean, no. You mean find the phase shift? You can't like this.
That's what I'm saying.
No, you have. That's why I
my
said which of. Yeah, sorry. That's why I asked from the beginning which of these 2 are easier to before you even look at anything, and that's what you have to say. That indeed, because the leading coefficient here is 1.
Oh, so we need.
If
we
you are
need one in
given
front of
if
that.
you are given this,
Right.
you have to pull it out before you find the phase shift.
Okay. Gotcha.
Yes, the leading coefficient must be 1. Otherwise, you are not going to be able to, you're not going to identify the phase shift correctly. So the phase shift is not negative pi.
Right.
You have to make sure that this is 1. So you have to pull it out.
Yeah,
So you will have 2 parentheses x plus pi over 2. Okay, let's look at one more for the same thing. So let's say 44. Y equals 1/2 tangent pi x minus pi. So I would like to identify the period and the phase shift.
So it would be negative period of 1.
So 1/2 tangent pi parentheses x minus 1. So the phase shift will be 1, and the period will be 1. Exactly.
What's the 1/2 do?
The 1/2 will do this.
Oh, okay. Vertical.
Right, meaning if this is tangent,
But
this will be
still
1/2.
Still a vertical asymptotes.
Oh, that will not change. Yes,
Yeah.
it will only be vertical stretching of shrinking of the graph. Okay, so now I would like to go back to 6.4 because we had some problems there that we didn't accomplish last time. Okay, and I'd like you to choose on page 468 as well as page 467. Anything you can think of between 3 and 36, 3 and 36, anything that has tangent in it, because we haven't discussed that. 3 and 36, and page 467, page 468. I see some tangent inverse between 3 and 6. I see some tangent inverse between 7 and 14. And on page 468, I see some problems with tangent.
Maybe 5.
Where do you want to start? Which one? 5. Very good. So we want to start with 5, and let's look at tangent inverse. So this is problem 5, part C, tangent inverse of the square root of 3 over 3. Remember, with tangent, we are looking here. Okay. So I'm looking at the square root of 3 over 3, and here's how I think. My professor specifically told me not to learn or study or remember or memorize tangent. But I know that there are only 2 options. For the small angle, 1/2 over the square root of 3 over 2 sine over cosine. And for the largest angle, the 60 degrees, is this. It cannot be this, because when I flip and I multiply, I get the square root of 3. So it cannot be the big angle. It must be the small angle. By the big angle, I mean 60 degrees. By the small angle, I mean 30 degrees. So that's why I'm saying don't memorize, because you really don't need it. So it's either 1/2 over this, and when you flip, you do get that, because you don't get this. So what angle has tangent the square root of 3 over 3?
30.
Very good. Or 30 degrees, whichever you want to write. And it's done. Now, 4C is more interesting. Tangent inverse of negative the square root of 3. Although I said try not to use or work with negative angles, but not in this situation. In this situation, I will have an answer here between negative pi over 2 and 0, because I'm asked to find the angle whose tangent is a negative number, which means it has to be a negative angle in the 4th quadrant. Okay, so now I'm thinking again, so it has to be a negative angle, and I'm thinking again, okay, tangent of the square root of 3. What can it be? Because I only have 1/2 over the square root of 3 over 2, or the square root of 3 over 2 over 1/2. And since it's not this, what can it be?
That one.
That one. So then minus or negative,
5 over 3.
that's it. And even if you don't want to, at some point in time, you will get in the habit of realizing what is the square root of 3 over 3 and which angle has the square root of 3 over 3 and which angle has the square root of 3. So this must be the big angle and this must be the small angle, if it has a denominator. Okay, what about 6C? Tangent inverse of 0. Between negative pi over 2 and pi over 2, there is only one angle whose tangent is 0. And that angle is the angle that has sine 0. Because only 0 over a number will be 0. Which angle is that?
0 degrees.
If I put 0 without the bubble, it's in radians. Otherwise, I would write this. So it's up to you. If you write 0 and nothing else, it's radians. Otherwise, if you want in degrees, you have to put a little sign. Okay, number 12. Tangent inverse of negative 4.